Hi, good day to you and welcome to my channel where I tutor you in science for free. The topic in this video will be DC circuits. And DC stands for direct current, which means to say the source comes in one direction from a certain outlet, say for example a battery. And this chapter is a build up on the previous chapter. If you have not seen it, please check out that video first. Then come back to this one. Okay, so this can be a little bit confusing, a little bit of imagination goes a long way. So let's get to it. Okay, so firstly, talking about circuit diagrams, you need to know how to draw them, know how to represent circuits and components in their various symbols and what do they mean, know how to read and interpret them, things like that. This is a list of all kinds of components, all kinds of wires and the like. More often than not, through a lot of exercises that you do, you realize that some are more popular than the others. And talking about circuits, electricity flows through them and electricity functions a little bit like a river current. That's why it's always a good tip to imagine that the electricity flowing through the circuit is like a river current, and river currents can flow and they can split and they can join back again. So the same like in an electrical circuit, you can imagine it like that as well. Water is coming out from a source in this direction and the same amount of water is going to be flowing through the pathway all the way around. In the series circuit like that, electric current is coming out from the positive terminal and it's going to be the same amount of current that is also flowing across. Okay, and in this example over here, this is a battery and the long one is the positive terminal, pretty easy to remember. Current comes out of it. Then A stands for ammeter, the component that measures the amount of current in the wire. R stands for resistors. So all of these are all lined up in a series fashion. And a resistor is like a stone that you put into a river. It blocks the amount of current that is flowing through. Okay, we'll talk more about that later. So in a series circuit, current is the same. So pretty straightforward. Okay, now we talk about potential difference. So potential difference and electromotive force we covered before. It's like talking about the height of a water slide. So I hope you have played with water slides before. Okay, a battery is like a tall giant pump that pumps water out in your water park. Okay, and in the circuit is like a little pathway that you can walk, and then the components are like little slides. The water is pumped upwards to a high height, okay, and then it flows down the slide of this R1 and another slide of the R2. So you can see the height of R1, water slide 1 and water slide 2 is going to be the same height as the overall height of the pump. So the voltage of a series circuit goes like this. The voltage of the battery, the so-called water pump, okay, is equivalent to the sum of the two water slides. And earlier we talked about resistance being like stones in the river. You can imagine it R1 like a small stone and R2 like another small stone. To simplify it, you can imagine it R1, R2 joined together to become a big stone. Okay, so yes, this chapter takes some imagination to make your life a little bit easier. Overall resistance, adding a stone, a big stone, equivalent to several small stones. In the series circuit, effective resistance is equivalent to the sum of its individual resistance. You can just add them up. Okay, however, in parallel circuits, a river is flowing from a water source outwards, and then once it reaches the branch point, it will split. Like nature, it does not necessarily have to split equally. It depends on what is happening in each branch of the parallel circuit. So if the resistance is the same amount of stone, the same size of stone there, then of course the river water is going to be split equally. However, if the resistances are different size of stone in the different river, then different amount of current is going to be flowing through them. By common sense, large resistance, small current. Like a big stone, you have less water flowing through. So in parallel circuit, total current flowing into or out of parallel branches equal to the sum of the individual currents of each parallel branch. And then they'll join back together to achieve the original amount of current again. Then it'll flow back to the battery. Okay, so now that's for current. We talk about voltage. So now we need to imagine water slide, right? So water pump is pumping water upwards into your water park, then water is flowing, and once it reaches the branch point, you can choose which water slide to take. Okay, so if you take one side, you slide down, or you take the other one, you slide down, you realize the height of these two is the same, and is also going to be the same as the one of your water pump. right? So if you visualize it like that, it's going to be a lot easier. Okay, so for voltage, the voltage of R1 and R2 is going to be equal to the overall voltage of the battery, or rather the EMF. Okay, however, for resistance in parallel branches, it's going to be a little bit different. It's going to have this little formula 1 over R equals to 1 over R plus 1 over R plus 1 over R, so on and so forth. So this is the odd one. I have no special story to help in this. So this is a little summary table of the differences between series and parallel. Don't have to particularly memorize this or commit to memory. Once you do lots of practice papers, lots of practice questions, and this will be pretty second nature to you. Okay, hope that wasn't too horrifying. So next we go on to potential divider. A potential divider is a circuit, a little circuit set up such a way whereby you can control how much voltage that is going to go out of this little circuit. So what do I mean? So your original electromotive force supplied by the battery is going to be of a certain value, let's say 2, and then if you want to control it to go out anywhere, any number between 0 to 2 through certain maneuvers, you can achieve it. Okay, so we are going to take a look at this now. So generally speaking, the potential divider is going to look something like that. The output voltage is the one that we are interested in. That's why it's called a potential divider. You are dividing the potential difference of the original potential difference. What's the big deal, right? The output one, what I like to remember is small over big multiplied by overall. That will be the ratio sequence you need to understand to determine the output voltage. So sometimes fixed resistors are used. So in this example, it's going to be like small over big. Your small is 5, your big is your overall, which is 15 plus 5. That's 20. So 5 over 20 times your overall will be 2 volt. Your output voltage for V1 will be as such. Okay, so conversely, on the other hand, V2 will be 15 over 15 plus 5 times 2. That's the output voltage. So pretty easy, right? Then complicated things can happen when there's a potentiometer. A slider is able to adjust the value by sliding over its resistor to give a variety of voltages, of output voltages. This is particularly useful for things like light, like sound, output components. Now with the use of a potentiometer, it gets a lot more visual. You can see exactly like how much the ratio, okay, small over big, okay, the small bar graph, it's like a bar graph, right? Small bar graph over the big bar graph multiplied by the overall voltage. Then you will get the output voltage. And of course, it's going to sound a little bit confusing now. We'll look at examples later. Okay, so next we talk about transducers. Transducers are components that convert non-electrical signals into electrical signals. So things like thermistor, light-dependent resistors are the common ones. This is the symbol. So for these two, a very good visual idea is, let's say for example, a light-dependent resistor. When there is no light, the resistance is high. Okay, so imagine your finger like the light energy. In times of bright light, light shines on the LDR. Okay, resistance is less. Okay, it's like a finger pressing down and making the stone smaller and smaller and smaller and smaller. So with small resistance, a small stone, more current is going to flow through, right? Similarly to the thermistor, in the event of low temperature, the resistance is going to be high. And imagine your finger like a source of heat. In higher temperatures, high temperature is coming into contact with the thermistor. Your finger is like coming down, pressing the stone, pressing down, 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 and the resistance gets lesser and lesser, more current flows through. So it depends on how the circuit is being set up. A variety of different outcomes can be designed. We can play around with heat and light for different kinds of outcomes using these two components. So you can use it in a potential divider when there is higher heat, okay, more current flows through, lesser resistance. So your small over big is going to be affected. Then you need to take all this into consideration. Similarly for the light dependent resistor, in times of more light, okay, then more current flows through, less resistance, your small over big is also going to be affected. The ratio is different. We'll look at some examples like that later. And that's all for the topic. There's really nothing much, a lot of components to learn. It's more conceptual. You need to learn how to imagine the water slide, imagine your river, imagine the stones. Okay, so we look at some questions right now. Diagram shows 6 identical lamps, 4 emitters and a battery. in the current in the battery is 1.5A, which ammeter reads 1A. So if the outgoing current, okay, like river current for this case is 1.5A, is going to be split equally between the 3 branches. Okay, each lamp has their own resistance, like little stones. So you can simplify the diagram into this. So of course 0.5 is going to be at each branch. The 0.5 exits the first branch, then the remaining 1 ampere goes out. So of course this is the ammeter that reads 1A. Next question. Circuit shown, ammeter reading 3A. What is the ammeter reading when a resistor of 2000 ohms is connected in parallel to the 2 ohm resistor? So of course you're going to throw your formula. Your effective resistance is going to be simplified to this. And you throw the next one, RVI, V equals to IR, okay? And you're going to realize that it's going to be this answer, slightly more than 3A. Okay, so potential divider, this is the one we were talking about. Okay, sliding contact S can be moved between P and Q of a 10 ohm resistor. Potential divider is connected to a 6 volt power supply, another 10 ohm resistor, like shown. Okay, so you can see now your small over big times overall is going to come to play here. What happens to the potential difference when X and Y, between X and Y, okay, the output as S slides from P to Q? It gets smaller and smaller from 3 volt to 0 volt. So firstly, you redraw your diagram to help you, okay, draw into this format. Then you realize that if the point is at P, then the voltage at the potential divider is going to be 3 volt because the resistors are the same amount of ohms. Then if you slide it lesser and lesser and lesser, okay, your small over big times overall is going to get lesser and lesser and lesser. Okay, so it's going to be from 3 volt to 0 volt. So if it's at Q, it's 0, right? So 0 over big times overall is 0. Next question. Okay, circuit drawn as shown. What is the reading on the voltmeter? So this is foundational question. We deal with the current one first. It's easy. So 2 little rivers you join become a big river. Then resistance, you use your 1 over R formula. Then you simplify the branch one. Then you add to this summarized stone to the other stone, your other resistor. Then you're going to get this value. Then V equals to IR. You're going to get this answer. So you realize many times circuits are drawn in all kinds of shapes and sizes and fashion, okay? Learn how to simplify them for parallel resistors especially, or resistors in series. Always help yourself by simplifying them or redrawing them, in fact, to help yourself visualize to your advantage. Okay, next question. This is an LDR component and a thermistor component in series with a battery. What conditions cause the potential difference across the thermistor to be the largest? So this is in fact a question on a potential divider, right? So you have 2 resistor kind of component and then they're asking you for the potential difference between one of them is like an output voltage, right? Largest, so you want the largest amount of resistance over here, so it has to be cold. LDR side has to be lower, right? So how do you have low resistance over here? You're gonna have light. So it's bright and cold. Circuit as shown, same. Total resistance of the circuit. So you can of course firstly join the series circuit, simplify the branch one using 1 over R formula, and you're going to get your answer. Calculate the current supplied by the battery. So you already have your overall resistance, effective resistance of the circuit. V, they give you have R, they ask you to count for I, so you're going to have V equals to IR. Okay, so state Y, potential difference between point AB is 3 volt. So you can see it's like a slide, right? The water pump pumps upwards, okay, current goes outwards, and then because the resistors are the same, the voltage is the same. So you slide down halfway, you slide down halfway, so it's going to be 3. It's going to be, the voltage is going to be shared equally, right? So the height of the slide is the same. Determine the potential difference between C and D. C and D, so you see, it's like a potential divider again, so small over big times overall. A and C, you take the difference between the height. So it's like different heights of different slides, right? In a water park, you're just determining the difference in the height. Okay, circuit as shown. Resistance of R1 increases to its maximum value. Okay, it's a rheostat, a variable resistor. Okay, then the potential difference across the lamp decreases from 12 to 2.9. When there's a potential difference of 2.9 across the lamp, the resistance of the lamp is 3.2 ohms. Okay, for this potential difference, calculate the current. So you have formula, right? I, V, you have R. Okay, next will be total resistance of the circuit. So they already give you the value. Total resistance equals to volt, 12 volt over the current that is in the lamp. You're going to get this value. Okay, a similar circuit is shown. This is of course a variable resistor. This is a potentiometer. You can slide the value of X nearer to B or nearer to A. Section XB has a resistance of 3.2. The total of R2 is 10. So calculate total resistance of the circuit. So finding AX, the remaining one, is going to be 10 minus 3.2, 6.8. Okay, you have to redraw it like that. So 3.2, 3.2, you parallel it, then you series it. Okay, you will get 8.4. Okay, state the potential difference across the lamp when slider X is at A and then at B. So if it is at A, it's the full value of the potentiometer, right? So your small over big times overall formula, your concept is going to be like what? Big over big, because it's the same distance, right? Because it's at the full value of 10. So 10 over 10 times 12 is going to be 12. Then if it is at B, then it is at 0 value. So 0 over 10 times 12. You're going to get 0. So state the advantage of using this circuit over the previous circuit. So this circuit, you can actually make the lamp go to 0 volt, which you are effectively turning it off. However, for the other one, you are not able to. You're just going to make it a little bit dim. Okay, student sets up this circuit as shown. Draw the diagram. So you can see sometimes you are asked to exercise this skill set. Long story short, this is going to be the answer. Take note of the orientation of the battery. Switch is closed. Then the lamp P has an ampere of 0.25, potential difference 1.5. Okay, calculate resistance of lamp P. Same, you have R, they're asking for R. You have V, you have I, throw formula. Resistor R, 18 ohms. Combined resistance of P, Q, R is 12. So what is the resistance of lamp Q? So of course you're going to reverse engineer or do your reverse working. You have the answer already. You just form your formula equals to the answer, then you work backwards. Explain in this circuit why the current in lamp Q is larger than in lamp P. So of course, like current, like real current, the current at Q is equals to the sum of the branches in the parallel circuit. It has a larger current. Q has different resistance from lamp P, even though they are identical lamps. Okay, because larger current flows through, and because lamps are non-ohmic conductors, it's going to be heated up faster than lamp P. So as a result, it's going to face a higher resistance than lamp P, as it becomes a higher temperature as compared to P, as Q operates at a higher temperature. And that is all for today. Hope you enjoyed this video. Do give it a like and subscribe, and share it with somebody who needs to see this. And I will catch you in the next video. Bye!